Okay. Now, algorithm for method 2. So, I have written everything. For example, when you will please see yourself once, if you get any term I have missed, so please let me know, but this thing algorithm I have made it for you only, right. So, read first you have to read the system data, the number NB is the number of nodes, total number of nodes, ln is the number of branch, then line parameters, that is your Rx, loads PL and QL at every node, then slack bus voltage V1, right, your magnitude of course, right. Here angles are not required. So, what I can do is I can make it its magnitude, right, voltage magnitude, and your then branch number JJ, that table you have to this thing, sending and receiving end also, sending end node ISJJ, receiving end node IRJ, all tabular form I have given to you. Then total number of nodes beyond branch JJ, that is NJJ I have given, total NJJ also you have to, all these things you have to read it in the computer, you prepare the data, take any network and do this, and total number of branches beyond branch JJ, that is BJJ also in this case you have to read. In the previous algorithm this was not there, and read matrix C same as before, but previous algorithm matrix F was not there, but you have to read this one also. Also said that total initially total power loss is 0 because convergence criteria, and SLQ is equal to 0, but when I will take the iteration thing I have to show only 2 iterations because not more than that. So, at that time I cannot show you the convergence thing, but if you do the third iteration, when I will solve it for you, at that time I will tell you to do that, right. After second iteration I will ask you to do the third iteration when you read this your what you call lecture, right. So, you set iteration count is equal to 0, I make it is green color I have written I2 is equal to 0. Now, step 2, initially set loss of all branches is 0, initially for the second method loss of all branches is 0, that is P loss JJ is equal to 0 and Q loss JJ is equal to 0 for all branches, JJ is equal to 1 to ln, ln is the total number of branches, right. So, step 3, for JJ is equal to 1 to ln total number of branches, if BJJ not is equal to 0, then compute PM2 and QM2 using equation 56 and 57 respectively. This is actually loss term you have to include in those branches, these two equations I have given, and if BJJ is equal to 0, this is B part, then compute PM2 and QM2 using equation 58 and 59 respectively, right. So, there also I have given, I have showed 58 and 59, basically it is a single term, but sigma term I have written in sigma form, but later next step I have showed that basically these are single term. First you make it, then step 4 A part, for JJ is equal to 1 to ln, M1 is equal to ISJJ, M2 is equal to IRJJ, you compute AJJ and DJJ, all these expressions are given using equation 68 and 69 respectively. One AJJ DJJ done, then compute VM2 and magnitude VM2 using equation 67, then you compute the voltage magnitude, because first this expression given, after that these two are given, right. Then this loop will be closed, end, right. So, here if you want I can put it some end, right. So, this is your for computation of this AJJ DJJ for JJ is equal to 1 to ln, right. Then B part, for JJ is equal to 1 to ln, right, when this is done compute P loss JJ and Q loss JJ using equation 72 and 73 respectively. This is also your what you call, this is also given, right. And C part, then compute total power loss, you sum up the power, equation it is not shown, but you just I have written in mathematics form that compute the all the branch power losses, the total loss, JJ is equal to 1 to ln P loss JJ, and similarly total Q loss, SP loss means sum P loss, that is why I am making SP loss, SQ loss is equal to JJ 1 to ln Q loss JJ, total reactive power this thing. Then initially total loss you set it to 0. So, dP is equal to, I am not putting any iteration number in the algorithm, just writing the step, but it is understandable. So, difference is absolute of P loss minus SLP and dQ is equal to Q loss minus SLQ absolute you take. And if both dP and dQ less than epsilon, epsilon some convergence criteria you set, if it is a per unit loss you can set 10 to the power minus 4 will be sufficient, or even minus 3 also will be sufficient, right. Then go to step 7, right. Then solution has converged, right, voltage magnitude, power loss, etc., etc. Otherwise, increase the iteration count IT is equal to 1, you replace SLP is equal to SP loss, SLQ is equal to SQ loss, and go to step 3. That means, you come to step 3, here you come, right, and it will go. So, this for this load flow, only few steps are there, very simple, and for this case, for a realistic size of your what you call distribution network, generally you will find it will converge in hardly 3 to 4 iterations, right. But note that it is not like a Newton-Raphson method, that Jacobian and other thing, nothing is there. Actually, network is radial, that is why its radiality structure of the network has been exploited to form such algorithms, right. But if you want to solve that your same network, radial network using Newton-Raphson method, that also can be solved, but the recommendation is that you use coupled Newton-Raphson method. Decoupled and fast decoupled will never converge, and decoupled also there is no chance that it will converge, right, because you will find that this radial network, they are very weak, this weak network. One branch is coming, maybe another branch or maybe another 1 or 2 branch leaving, right. So, those things are beyond the scope, but in this course only we will see this method 1 and method 2, but not the Newton-Raphson method. So, do not try to solve for this course anything on Newton-Raphson method, right. So, this is the algorithm. Now, we will take an example. First, we will take the example of method 1, right. So, in this case we did not take any lateral branches, otherwise in the classroom it is not possible to, if you take lateral branches. So, number of nodes will be increased, and it is very difficult actually time consuming process, right. But when we will put the assignment during this course, we will give you some only 3-4 nodes example we will give, but we will try to add one node as a lateral branch, one branch as a lateral branch, right. So, anyway, so these examples I have taken, that this is for method 1 only. Method 1, same example will solve using the method 2, such that you will know the difference between these two methods, right. So, this is substation, this voltage is V1, V2, V3, V4, and impedance is Z1, Z2. Let me tell you one thing, whenever V suffix 1 and V bracket 1, they are same thing, but when putting in the diagram, instead of bracket I am making like this, such that it will take less space and looks does not look clumsy, right. So, this impedance of this is branch 1, current is I1, green color one, this is I2 capital, and this is capital I3 branch current, and this is impedance Z1, Z2 and Z3 branch impedance, right. And every load is there, PL2 plus JQL2. So, current going through this load is I2, PL3 plus JQL3, current going through this load, actually our load is drawing current I3. Similarly, I4, that current going to the load is I4, that is PL4 plus JQL4, right. Data, substation voltage is a slack bus. So, V1 is 1 angle 0 is taken per unit, actually this is you take, it is a 11 kV feeder, and base voltage here it is a 11 kV feeder you take. So, substation voltage V1 actually 11 kV in real unit, and base voltage you take 11 kV, and base MVA, right, that is 100. So, sometimes we can, I will write this one is equal to MVA base, right. So, is equal to 100, that means V1 is equal to 11 by 11, that is 1 per unit. So, that is why V1 is equal to 1 angle 0, that is 1 per unit. Now, Z1 it is given 0.78 plus J 0.45 ohm. These are all ohmic value, we have to convert it to per unit values. Z2 is equal to 1.62 plus J 0.66 ohm, and J3 is equal to 2.19 plus J 0.91 ohm, right. And loads are given here, I have written, I think everything is readable, I am reading for you. Load here PL2 plus JQL2 is equal to 400 plus J300 kVA. This is kilowatt, this is kilowatt, but when you take combination, this is we call kVA. So, PL3 plus JQL3 is equal to 500 kilowatt plus 400 kilowatt. So, 500 plus J400 we can say this kVA, and PL4 plus JQL4 is equal to 600 plus J400 kVA. So, these are the load, right, it is given, but this one is, this is actually PL2 is 400 kilowatt, PL3 is 500 kilowatt, PL4 is 600 kilowatt, and QL2 is equal to 300 kilowatt, QL3 400 kilowatt, and QL4 is 400 kilowatt, but their combination is kVA. Base impedance ZB is equal to kV square by MVA base. So, voltage base is your 11 kV. So, it is 11 square upon 100. So, base impedance is 1.21 ohm. So, this impedance you divide by ZB 1.21 you divide, right. Then it will be converted to per unit first. Therefore, Z1 is equal to per unit if you make, that is your 0.78 plus j 0.4 upon ZB. So, 0.78 plus j 0.4 upon 1.21. So, it is coming 0.7442 angle 30 degree. This one you have to make it again R1 plus Jx1. I did not do it here, but later I have taken this value. Similarly, Z2 you will get 1.4456 22.16 degree. This is given in ohmic value divided by base impedance. Similarly, Z3 per unit value is equal to 2.19 plus j 0.91 upon 1.21, it is 1.96 upon 22.56. That means, your R1 per unit actually 1.62 upon 1.21 and sorry R2, and X2 is equal to 0.66 upon 1.21. Similarly, for R1, similarly for R1 X1 for and R3 X3. So, this is your impedance per unit conversion. Then the load is given in kVA. So, that means first you make it to MVA, then divide this data by 1000. So, it is become 0.4 plus j 0.3 MVA, right. This way you make it, then this is kVA, you transfer it to MVA, and then you divide this thing by base MVA 100. You divide this PL2 plus j QL2, then 0.4 plus j 0.3 by 100. So, it will be 0.004 plus j 0.003 per unit, right. So, similarly, PL3 plus JQL3 is 500 plus J 400 kVA. You can write this one as 0.4 plus J 4.4 MVA, divide this by 100. So, PL3 plus JQL3 will be 0.005 plus J 0.004 per unit, right. Similarly, PL4 plus JQL4 is equal to 600 plus J 400 kVA is equal to 0.6 plus J 0.4, that is MVA. It is divided by 100. So, PL4 plus JQL4 will be 0.006 plus J 0.004 per unit, right. Then separately I think separately I have written next PL2 and QL2. Therefore, your PL2 is equal to PL2 plus JQL2, if you write, it will be 0.004 plus J 0.003 is equal to 0.005 angle 36.87 degree per unit. So, that because why I have written the conjugate of this one, because when you will compute the load current, this PL2 minus JQL2 is required. So, that is why PL2 minus JQL2 is 0.005 angle minus 36.87 degree. Similarly, PL3 plus JQL3 is equal to 0.005 plus J 0.004, that is equal to 0.0064 angle 38.66 degree per unit. So, it take the conjugate. So, PL3 minus JQL3 will be 0.0064 angle minus 38.66 degree. This conjugate as I am taking because we need to compute the load current. Similarly, PL4 plus JQL4 is equal to 0.006 plus J 0.004 is equal to 0.0072 angle 33.69 degree per unit. Therefore, PL4 minus JQL4 is equal to 0.0072 angle, it will become minus 33.69 degree per unit, right. So, that means loads impedance all computed in per unit and their conjugate I have taken. Now, flat voltage start. So, V2 is equal to V3 is equal to V4 is equal to V1, you take 1 angle 0, all the initial voltage of all the nodes we start with 1 angle 0, right. But ultimately, because you have to find out your what you call that initial current at the node 2, right. So, I2 will be PL2 minus JQL2 upon V2 conjugate, but node 2 load current at node 2, node 3 and node 4 you have to compute. So, small I2 is equal to PL2 minus JQL2 upon V2 conjugate. So, PL2 minus JQL2 have got it 0.005 we have computed minus 36.87 degree by 1 angle 0, conjugate 1 angle 0 or 1 angle or without conjugate same thing. So, 0.005 angle minus 36.87 degree. So, I2 is equal to actually 0.004 minus J 0.003 per unit. This is for load current at node 2. Similarly, at node 3, I3 is equal to PL3 minus JQL3 upon V3 conjugate. So, anyway it is a flat voltage start. So, voltage 1 angle 0, right, and 0.0064 angle minus 38.66. So, that is actually same thing 0.0064 angle minus 38.66 degree. So, it is I3 is equal to then 0.005 minus J 0.004 per unit. This is load current at node 3. Similarly, load current at node 4 small I4 PL4 minus JQL4 upon V4 conjugate. So, it is 0.0072 angle minus 33.69 degree upon 1 angle 0. So, that is actually 0.0072 angle minus 33.69 degree, and that is I4 is equal to 0.006 minus j 0.004 per unit. This is actually your what you call that all initial load currents you have computed. I did not put any iteration number as a superscript or anything, but iteration 1, iteration 2, this we will proceed, such that things will look this thing will look better on the your what you call on the paper, right. Now, current through branch I1, look at this your just hold on this example. Look at this example, I1 is equal to I2 plus I3 plus I4, small I2 plus small I3 plus small I4, right. So, I1 is equal to I2 plus I3 plus I4. So, this is I1, this is I2, this is your this is I2, this is I3 and this is I4. So, sum it up all, it will become 0.015 minus j 0.0. Here I am not making in bracket, right, but meaning is same, just for the your classroom exercise I made it like this. So, if you made it, it will become 0.0186 angle minus 36.25 degree per unit, right. Similarly, I2 current through this branch I2 is equal to small I3 plus small I4. So, I2 is equal to small I3 plus small I4, that is I3 is this much, I4 is this much. Previously in previous slide we have computed all. So, if you make it I2 is equal to, ultimately it will come 0.0136 angle minus 36.03 degree per unit, right. And last branch, that is I3, same current going to the load, I3 is equal to I4, right, because there is no other branches beyond that. So, I3 is equal to small I4 is equal to 0.006 minus j 0.004 is equal to 0.0072 angle minus 33.69 degree, right. So, all initial load current, then these are all initial branch currents are also computed. Now, voltage calculation, from this one V2 is equal to V1 minus I1 Z1 from this first branch. So, V2 is equal to V1 minus I1 Z1, V1 1 angle 0 minus I1, I1 is this much, your the I1 is this value. So, put it here into your Z1, Z1 we have computed earlier, right. From here only Z1 is computed here, right. This is Z1, this is Z2, this is Z3, all have been computed. So, put here Z1, right, and you simplify, you multiply then simplify, then what will happen, all I have written here for you, you can check, right. V2 will actually will become 0.98625 plus j 0.0015 is equal to 0.98625 angle 0.087 degree per unit. Look, this angle is small. Here I will put a question to you that you will answer, I will not answer. Generally, when you are solving any transmission network or this that, you will find that voltage angle generally lagging, yes, I mean negative, it becomes negative, right. Distribution case, it may happen that it may be negative, it may be positive also. Why this is happening, right? Why it is why this positive angle is coming, whatever it may be, it is very small, I told you, very negligible, but why this positive angle is coming? See the problem carefully and then you tell, right, data, look at the data, and from that what is your observation, and based on that you tell me the answer. If you write the answer, then I will appreciate when you will go through this, but angle is coming positive 0.087 degree. Actually intentionally I have taken like this, such that but negative also can come, it depends on the something, right. So, that something is there in the problem. So, you have to answer this, right. So, I am leaving it for you at the beginning, right. So, then we will compute then your V3. So, V3 actually straightforward, V3 will be then V2 minus I2 Z2. So, this but this V2 now you have computed, right. Do not use for voltage calculation, do not use that flat voltage, use the immediate, the voltage which you have got now, this voltage you have got V2 immediately, this V2 you should use in this expression. For current calculation, all the flat voltage are required, because you have to calculate the load current, without that you have no other way. But when calculating V2, this V2 you put it, this V2 you got it, this V2 you got it, this one you put it here, right. So, and minus I2 is this much already calculated before, and Z2 is this much, right. So, multiply and simplify, then you will get your, after making all simplification, I suggest you make all these things, then V3 is equal to, you will get 0.96718 angle 0.376 degree. Here also it is positive, right, angle is positive, it is per unit. Similarly, your V4 is equal to V3 minus IZ3, this V3 use, that means this value use. So, that is 0.96717 plus j 0.0062 minus your I3 is this much we have computed before 0.0072 angle this one into Z3 also in per unit we have computed this one, multiply and simplify, right. If you do so, then V4 will become 0.95333 plus j 0.00892. So, 0.95334 angle 0.53 degree, right. So, this is V4 after first iteration, that means after first iteration these are our voltage, V2 is equal to this one, V3 is equal to this one and V4 this one. Using this voltage now we will compute the new value of the load current in the second iteration, right, in the second iteration. Now, using this voltage, now you compute I2 is equal to PL2 minus J equal to V2 conjugate. This value is unchanged, PL2 QL2 will be unchanged, but V2 will be changed. So, it is your V2 is this much, its conjugate will be minus 0.087 degree, I have taken that, and after simplification, right, after this one we get U is equal to this one you write, and then you get 0.00406 minus j 0.003035 per unit. This is I2 in the second iteration, right. Then I3 is equal to your PL3 minus JQL3 upon V3 conjugate. This V3 use, so it is 0.0064 angle minus 38.66 degree divided by 0.96718 angle minus 0.36 degree. If you simplify, it is the thing, and then if you make that real and imaginary part, I3 is equal to 0.0051928 minus j 0.004101 per unit, right. Similarly, I4 is equal to PL4 minus JQL4 upon V4 conjugate, this voltage is used, right. If you do so, it is coming this one, this is already known. So, divided by this V4 conjugate 0.95334 angle minus 0.53 degree is equal to this much, take it dual imaginary. So, it will be 0.006322 minus j 0.00413 per unit, right. So, initial load currents are computed as second iteration. With this load current, now you compute the branch current. So, I1 capital I1 is equal to small I2 plus small I3 plus small, this already we have computed just now, right. You substitute all and then you add it up, it will become actually I1 capital I1 is equal to 0.01922 angle minus 35.88 degree per unit. Similarly, I2 is equal to, right, I3 plus I4, right. So, this is your what you call I2. So, I3 and I4 you substitute and simplify, it will become 0.01415 angle minus 35.55 degree. So, and last one I3 is the last node. So, I told you earlier I3 will be simply is equal to I4, it is 0.00755 right angle this one. So, and all this capital I in the second iteration we got it. With this voltage calculation we have to proceed. So, voltage calculation for second iteration, V2 is equal to V1 minus I1 Z1, V1 voltage was known to us as slack bus voltage 1 angle 0, I1 is this much we have computed and Z1 already known to us. So, multiply and simplify, right, you will get V2 is equal to, just you do it yourself, hope all these calculations are correct, but from my side I have to tell you, please see once, right. Hope I have made all this correction because all this your what you call all these things have been solved by me only. So, if there is any error you calculation or anything, you just let me know, and if you find anything I will appreciate that, right. So, then V2 is equal to 0.98578 angle 0.085 degree. Similarly, V3 is equal to V2 minus I2 Z2, already we know that from circuit diagram. So, V2 is this much, this V2 you use here, this V2 you use here, minus I2 already we have seen this much, right, 0.01415 angle minus 35.55 degree into this is the impedance, right, that is the Z2, this already you have computed. So, you simplify, you will get V3 is equal to 0.965882 plus j 0.0062019 and or V3 is equal to 0.96590 angle 0.36 degree, right. Next is that V4. So, V4 is equal to again V3 minus I3 Z3. This V3 just now we have got it, right, in the previous page I have shown you, minus this is I3 into this is Z3. So, you just multiply and simplify, right, you will get V4 is equal to 0.951 333 plus J 0.0089247. So, V4 is equal to 0.95137 angle 0.5 degree. So, after second iteration, this is my voltage magnitude, right, it is 0.98578, 0.96590, 0.95137. What I suggest, I have done up to second iteration. So, in the classroom this is sufficient. I will request you, please do one more iteration, third iteration, because after 2 iterations generally in this method solution does not converge. Generally convergence I cannot show you here, because only 2 iterations I have done. You make 3 iterations and see the difference of the losses, total losses. How you will calculate the total losses? I will tell you something here, right, that how to calculate losses. This power loss after second iteration, right. First I will explain it here. Suppose you have a network, a radial network, right, it is a radial network, right, it is a radial network. We have taken 4 node example, 1, 2, 3, 4 node example we have taken. Everywhere loads are there, I am not showing anything, loads are there, loads are there. This is your PL2 plus JQL2, this is PL3 plus JQL3, this is PL4 plus JQL4, right. And this is substation, right, and power is being injected here, right. This is your PS plus JQS, this power is coming from the grid and going to the distribution network. This is substation, earlier we have explained everything, and these are the branches, these are the 3 branches are there, 1, 2, 3. Then what is the power injected to this substation? It will be actually, it will be total load plus the loss. That means PS is equal to your PL2 plus PL3 plus PL4. This is the power injected, right, in substation. This is the load, it because it and it will be loss also. That means P loss branch 1 plus P loss branch 2 plus P loss branch 3. This is the power, incoming power from the substation, right. Similarly, that means your total loss P loss 1 plus P loss 2 plus P loss 3, that is the total loss of the network, right, is equal to your PS minus subtract all the loads PL2 plus PL3 bracket close. So, total loss will be PS minus this thing. Similarly, for reactive also Q loss 1 plus Q loss 2, same thing Q loss 3, because substation has to supply total reactive load plus reactive loss. So, Q loss 3 is equal to QS minus QL1 plus it is actually QL2, QL3, it is 4, actually 2, 3, 4, sorry, it was no 2, 3, 4, right. So, here I have written, so it is PS minus PL2 plus PL3 plus PL4, then it is QS, then QL2, then QL3, then your QL4, right. That means whatever injected power subtract the load, that will be the total loss. This thing is understandable, right. So, how to calculate, how to compute this? From this diagram only we will write, from this diagram. So, current flowing through this branch is say I1, this is I1, right. Therefore, what you will do, so substation voltage V1 is known. In general, if it is different does not matter, it is 1 angle 0, right. If it is 1 angle 0, that means you can write that power injection PS minus JQS is equal to, right, is equal to your V1 conjugate, then this I1, this is the current in this branch, capital I1, chi I1, right. V1 is 1 angle 0, so that means conjugate is also 1, that means PS minus JQS is equal to actually I1, right. That means P, it is in per unit, that means substation power PS is equal to real part of I1, right, and substation power QS is equal to your minus imaginary, right, I1, because minus sign is there, that is why you take QS is equal to minus imaginary of I1, right. Whatever it will come multiplied by this corresponding base value and everything, you will get the real quantity. This is the power injected from the substation, right. Then what will be the loss? If you have so many nodes and this thing, therefore, your total P loss, SP loss will be is equal to PS minus PL2 plus PL3 plus PL4, right. Similarly, SQ loss will be your QS minus your QL2 plus QL3 plus QL4, right. This is small network. In general, SP loss is equal to power injected at the substation PS minus, suppose you have n number of nodes. So, I is equal to 2 to NB, we can make PLI. Similarly, S total Q loss will be is equal to QS minus your I is equal to 2 to NB, then QLI, injected power minus the total reactive load and injected power, real power minus total real load is equal to this P loss, Q loss. This way we can calculate the your what you call the substation your power loss, right. First substation injected power, then power loss. Of course, another thing is there that every branch R1 X1 R2 X2, that is I, here it is current I1, here it is I2, here it is I3. So, I1 square R1 plus I2 square R2 plus I3 square R3, that is also valid, and this one also valid, but this one is the easiest one. I think you have to appreciate that this is the easiest one, right. Thank you again, we will be back.